2 years ago, CERN started the Beamline for Schools competition, allowing schools from around the globe to enter a research proposal for the chance to win experimental time on the T9 beamline of the proton synchrotron. Last year, our team, Accelerating Africa, consisting of 8 scholars from St. John's College and 2 scholars from Bernardsson Park High School, was led by Dr. Colleen Henning and Professor Simon Cannell in the project to source crystal undulator radiation. In collaboration with Element 6 and ESRF, we were invited in September last year to go to CERN to carry out our experiment. Because of the highly penetrable properties of high-energy radiation, it has numerous applications in the fields such as material biology, material science, and molecular biology. It is for this reason that our team decided to conduct research in this field. At the moment, coherent photon radiation is produced comfortably at about 10 keV. This is currently done by using large dipole magnets to cause charged particles to undulate and therefore accelerate. The acceleration allows the particles to produce photons. However, in order to produce energy of higher, in order to produce higher energy radiation, the use of dipole magnet undulators, as is currently the situation, is impractical because it is space consuming and it requires long distances for the particles to undulate and accelerate. Also, because the particles cannot be accelerated at a high enough rate, the high energy photons cannot be produced. The graphical representation on the left shows the photon peak brilliance versus the corresponding energy for multiple synchrotron facilities around the world. It shows that while high photon peak brilliance is possible, achieving high energy radiation is not quite as possible. Importantly, the plots on the top show free electron laser radiation, which are lasers that are able to produce coherent photon radiation, where the waves of the electromagnetic radiation are in phase. Our crystal undulator, which produce high energy radiation, at the moment we haven't really aimed for producing coherent photon radiation, but in the long run we would like to. So consequently, because of the dipole magnets being insufficient to produce the high energy radiation, the use of sources such as the crystalline undulator have been investigated for producing high energy radiation. The principle is that the particle undulation occurs when particles pass through a crystalline lattice that has a modified channel of undulating channels. Because of the regular alignment of the atoms within the channels, the incident particles travel in transverse oscillations along the shape of the channel and therefore accelerate as they go. More importantly, because it's not a regular straight channel, because of the the undulating shape of the channel itself, a secondary undulation can occur if the particles enter the channel highly aligned and therefore produce radiation. Crystal undulator technology is still relatively new. A crystal undulator can be made either by infusing layers of boron into a carbon lattice or germanium into a silicon lattice. We had Element 6 grow our diamond by chemical vapor deposition, whereby in the gaseous phase of growing the substrate of the undulating diamond on top of the original diamond, boron gas is infused into the mixture so that it is deposited. The undulator is formed by constraining the diamond in 2 of its 3 dimensions, whilst the boron gas is infused, so that the restrictions allow the crystal only to expand in the direction of one of its planes. As you can see in this diagram over here, the direction of the 110 plane of the diamond is diagonal to that of the 010 and the 110 crystallographic planes. The 110 plane of the diamond is the best plane for channeling because it is the most open channel for the trajectories to pass through. It is therefore on this plane that we allow the undulating to occur. So, if you allow the diamond to swell in the direction of the 100 plane, the result can be seen in the image on the right, whereby the channel of the 110 plane undulates. The extent of the swelling can be calculated as seen on the equation above, where delta A is the increased length of the lattice, as shown in the red line, and A0 is the initial length of the lattice. These diagrams here show the original diamond with the grown substrate on top, which is the undulating part of the diamond. As you can see, in order to get the particles to undulate through the crystal, they have to be incident at the correct trajectory through the 110 plane. If you look at the angle, the crystallographic spectrometer over here, you can see exactly where the 110 or 011, as indicated in that photo, is situated if you rotate the crystal. This is Team Accelerating Africa. We decided that the name was appropriate because this experiment acted as an opportunity to contribute to the status of science education in South Africa, and because the name represents our objective in accelerating positrons. We also thought that since scientists enjoy, well, they have a good sense of humor, that they would appreciate the pun, as long as our name was not shortened to AA. This is the setup of the T9 beamline. It can be categorized as a tagged photon detector because we were able to track individual positrons that pass through the beam with relevance to the photons that they emitted along the course of the beam. So initially, starting with the target that is on the proton synchrotron, the main accelerator for our beamline, the incidence of protons hits the target and spills a variety of particles, kaons, pions, muons, positrons, and all of their antiparticles. Then it is the job of the sweep magnets to ensure that only the particles within the energy that we had specified, whatever it may have been for that specific spill, that they were accounted for. The energies that had a momentum that was too great or too low were not included. Then the collimator consisted of quadruple magnets that focused the beam on the target position so that the particle incidence there was as narrow as possible. The two Cherenkov detectors were important because they were set to record positron incidence, as there was a whole variety of particles passing through here despite selecting only these specific momentums. Then the delay wire chambers offered us the precise Cartesian plane-like graphical coordinates of the particles' trajectories as they passed through them, whilst the scintillators gave us they confirmed the presence of the charged particles as they moved through them. The delay wire chambers were highly important, especially the first two, because the particle incidence consisted of a whole lot of positrons that were moving in all sorts of trajectories. And for our undulator, we would like particles that were highly aligned to move through the undulator. So it was important to use the delay wire chambers to make sure that we could select only the positrons that were moving parallel to the beam direction. Importantly, the second scintillator over here was a veto scintillator, which meant that it had a hole in the center so that we could select only the positrons that passed through that hole, able to reduce the size of the beam and remove the noise. As the particles passed through the crystal undulator, those that entered the particle within 50 microradians parallel to the beam undulated. And then the sweep magnet wiped away all of the charged particles, such as the positrons and other intrusive particles, from their course so that only the photons that were radiated from the undulator continued along their course to have their energies read by the photon calorimeter without disruption from the other particles. The particles that were deflected by the beam magnet had their energies read by the final calorimeter, whereby we could assign identities to the particles based on their energies by calculating their mass. The last delay wire chamber and scintillator were important to us because we created a projection of where the particles should have been so that we could correlate the positrons that radiated and those that did not based on their incidence on the last delay wire chamber. Importantly, we used positrons rather than electrons because positrons stay channeled within the undulator longer than the electrons based on previous experimentation. And we were quite lucky to have a beamline in which we could use positron incidence rather than electron incidence for this matter. Other experiments with a similar aim to ours have not had this opportunity. Also, because the proton synchrotron is able to deliver energy spills of higher energies, higher than most accelerators could offer, we were able to use, of course, energies within 1 to 10 GeV, where the undulating radiation requires a beam greater than 1 GeV, because an energy of an electron beam of an energy that is moderate is insufficient. Okay, so these are the results that we should have expected from our undulator. It shows here you get the beam energy of the original incident beam, and if we were expecting channeling radiation, we should see energy peaks at around 37.8 MeV. And for undulating radiation, we should expect a peak of 370 MeV. We used a short amplitude and short period undulator, which meant that the undulation wavelength was 600 nanometers as opposed to 10 micrometers. This is because we wanted to see the undulating peak at 370 MeV rather than 10 MeV, so that we could differentiate it from the noise of the other particles. Here you can see just how much more effective the positron incidence is when opposed to the electron incidence. This is the photo taken of the undulator alignment within the beam, looking downstream of the beam. The goniometer is situated just before the second delay wire chamber and scintillator. The longest part of the experiment, of course, was calibrating the beam itself. Firstly, we ensured that the delay wire chambers were operational and that they were calibrated within reference to one another. So this plot over here shows the X position of delay wire chamber 1 versus delay wire chamber 2, and you can see how proportional the results are, meaning that the particles that passed through the first delay wire chamber passed through just about the second delay wire chamber in about the same place, meaning that they were very well calibrated to one another. The image below shows the projection that we calculated of the last delay wire chamber. So this is not actually where the particles pass through the delay wire chamber, but where we would have predicted it to have been based on the first two delay wire chambers, which was incredibly important for creating a plot between the actual versus the theoretical incidence of the particles after the sweep magnet. Then we ensured that the beta scintillator was operating efficiently, and it seems to have done so, including mainly only the events that passed through its center. This was useful so that we could remove the noise of the beam. As you can see here, we've cut specifically on the particle incidence that was in the center of the beam, because those trajectories would have been parallel to the beam. Then one of the challenges that we faced during the experiment was the selection of relevant data. Because of all the beam detectors and the long flight path, there was a significant amount of Bremsstrahlung radiation. This can be seen as a distribution along the graph here, with a characteristic peak below 1 GeV as well. On top of this, we accounted for a large muon count, judging by the high particle incidence over here, and the last peak accounts for positrons. The energies over here were not calibrated, so they're not very relevant to the data, although this should be at about 1 GeV, and the muons at around 370 MeV, which was a problem. We had to reduce them because that's where we would expect to see the undulating radiation. The red line represents the noise that we excluded, the black line is the relevant data, and the blue line is the incrementation of the two. Finally, with the data that we collected with the remainder of our time during the experiment, we managed to create an angle space plot of the particles that entered the undulator. Before further selecting and refining the data, you can see that the power spectrum plot of the energy output is relatively flat, meaning that there was a high Bremsstrahlung count, as this is plotting the energy versus the particle incidence multiplied by the energy, and where a Bremsstrahlung curve is kind of looks like a 1 over E distribution. If you multiply the number of particles multiplied by 1 over E, multiplied by E itself, it should be around 1, so it should be flat. Despite this, when we selected the particles that would have passed through the undulator coherently, we are able to see an energy peak at about 370 MeV, where we would expect it for channeling radiation. And the subsequent peaks suggest coherent Bremsstrahlung radiation, which is in favor of our prediction that the undulator would produce radiation. So we were able to efficiently calibrate our beam using the Atlas data acquisition code, reject the background noise, excluding all the muons so that we could see the relevant data. And yeah, unfortunately we encountered two major problems where the delay wire chamber angle resolution was lower than we expected, and the length between the first two delay wire chambers was not great enough to compensate for this, as well as a high emittance rate of the particles where the beamline was broader than we would have hoped for, so therefore reducing the number of particles that would have entered the undulator coherently. So finally, we were actually invited to return to CERN as we did not have sufficient time to complete to obtain useful results for our experiment. So we decided to come up with a few improvements, one of which being moving the second bend magnet after the two Cherenkhovs, which would be useful so that we could sweep away the remainder of the useless, or the particles that were not useful to our experiment after we had detected the positrons. Then we would use a vacuum flight to reduce the amount of air that the particles have to pass through, and therefore reduce the amount of Bremsstrahlung radiation produced thereof. Just to stabilize the temperature of the crystal for better results. The goniometer, because we weren't actually sure that our angle of incidence was correct for the undulator, because the goniometer was a little bit unstable. We would like to have a more definite confirmation that the angle is correct. We would use a different photon calorimeter, more accurate, and of course we would increase the distance between the two delay wire chambers, and therefore the resolution of the delay wire chambers would not stunt our calculations. And yeah, so we've decided that our experiment is feasible, and that we went to a whole lot of complex lengths to get to the results that we got to, but above all, we were satisfied with the method that we used, and hopefully we will be able to go back to CERN and receive some results that are groundbreaking. Thank you very much.
Yes, Brandon, any questions?
Yeah, I'm very impressed with what you did. My God, you were just in high school and you managed that. It's amazing. Was the equipment that you were using, was it satisfactory? Was it at the level that it could be easily used and all that?
Actually, no. There were a few complications during our experiment. So one of them being that as the winners of the T9 of Beamline, we were sharing it with an Italian team actually. So firstly, anything that we wanted to change on the Beamline had to run through their experiment, which was running at the same time. So a few times we had our suggestions rejected by them, and also we complained a few times before we actually went to CERN that we wanted, for example, a greater length between the delay wire chambers, and we wanted to remove one of the Cherenkhovs or move the sweep magnets, but they denied it at first. So it was mainly because they didn't allow us to make the changes to the beamline that we were restricted. So we did actually predict the problems with the apparatus before we started.
Okay.
Any other questions?
I didn't perfectly understand where the veto scintillator.
Oh yes, sorry about that. So the veto scintillator, this over here, yeah, the veto scintillator is the green line. So you've got the undulator, which is the target position, and then after that, the veto scintillator and the second delay wire chamber. Yes.
When you said you're going back, but you're not sure when you're going back.
Oh yes, we've been asked to submit another paper, and then they'll review it, and if it's successful, we can write a proposal, and they may offer us time to go back.
Okay, so you may go back.
We may. I mean, there's the possibility, but we haven't quite decided.
Great. Let's thank Brandon again.